Thank you. And it may seem a little strange to talk about the kind of boats we're going to talk about today based on my day job spending and some nights spending on oil rigs and other things. But I think a lot of naval architects have a fascination with technology and the ocean. So whether it's oil rigs or kayaks, for me there's a lot of commonality. And of course, as I read the quote and I thought that was a pretty good quote, and then I realized I wrote it many years ago, but I think it's really true. Because we can go back in history to some remarkable technology that predates the scientific age. And even today, I think a lot of times technology comes before the science that explains it. And I'll talk a little of that. Just a starting point, this is a little fishing village in the west of Scotland. I come from Scotland. This is my wife's home village. And that boat in the foreground was built in 1898. So it's over 100 years old, and it's a small version of a Loch Fyne skiff. And any of you that have ever enjoyed kippered herring in the UK, it probably came from this little fishing port. We're talking about, there's some words here. I don't know if I invented the word ethnotechnology, but I was lucky enough early in my career, because I moved from Scotland to Canada, and I was a naval architect, that the Food and Agricultural Organization of the United Nations, which is based in Rome, thought I would probably speak French. And they had a need for francophone naval architects in funny parts of the world in Southeast Asia and Africa. So I ended up in a place, and I went out full of vigor to do good things in the world. And then I found I learned a lot more than I taught. So I'm going to talk a couple of things here. But it's really about we should not be blinded by our science and our technology here. There's a lot of that around in lots of parts of the world, and if you open your eyes, there's things we can learn from that. As a Scotsman, at least born a Scotsman, I can see that, for example, and I went to Glasgow University where both of these gentlemen were. James Watt didn't exactly invent the steam engine, but he perfected it in the late 1700s, and I think there's no doubt that that really changed the world. Basically changed the world from the developed world from an agrarian economy into an industrial economy. But it was almost 100 years later before Baron Thomson, Lord Kelvin, actually defined how those things worked in a scientific sense. And that's just one example. I think we can think over and over of the technology preceding the science. For those of you in the offshore industry, we developed over the years deep water spars. And we put them in first, and then we discovered something called VIV, vortex-induced vibration. So then we got the science right and fixed it. But there's a lot of examples. This is slightly tongue-in-cheek, but this is one of my pet projects with my day job. It's we call it Project Rotten. It's a riverine oil tanker in Nigeria, but it's got a lot of the features we look at: a biodegradable hull, a low emissions propulsion plant. The particular thing I like is the automatic wake suppression, because of course these operate in riverine environment where wash along the banks is pretty critical, and it's just allowing the right amount of oil to leak out to suppress the wake. You've seen this quote already, so I won't go back to that. I'm just going to touch on a couple examples of things that I've dealt with in the years. And one is a skin boat, but from the same part of the world as the ones before you. In fact, I'm going to talk more about Alaskan, but in a circumpolar bit. But an umiak, which today we still use in Alaska, or the Alaskan villages use for whale hunting, and I get up to Alaska quite a bit to the northwest villages. So I want to talk a little bit about that and some things we can learn. And the bottom ones are basically dugout log canoes from Nigeria. The umiak is a skin boat, usually walrus skin, that are used by the native villages, Barrow, Wainwright, Point Lay, Point Hope. And in fact, my company has been instrumental in Point Lay, which is, if you look it up on the map, you'll find it's about halfway from the Bering Strait to Point Barrow, had stopped whaling because they didn't know how to sew walrus skins anymore. And so 2 years ago, we brought ladies, because it's always ladies that do the sewing, from Barrow to Point Lay, and they showed how that was done, and this year they got their first whale in several years. So I'm quite proud my company saw the value in that. But from a naval architect's point of view, the thing that fascinated me was the fact that they always use female walrus skins, and I found that out by chance talking to them. And it's such an obvious reason, but it's not obvious till you're told, is that the male walrus fight, and male walrus have big tusks, and when they fight, the skin gets scarred. And as any good naval architect knows, if you put a membrane in tension and it's got anomalies in it, it's probably going to tear. But the native builders of Umiaks learned that a long time ago, so they chose the right skins to use. And these are just some examples of current conditions. The bowhead whales are hunted. As part, again, of my day job, we're looking at having some drilling in the Arctic, so we are now tracking whales by GPS. And of course, the local hunters who are traditional hunters all have GPS tracking devices. And so there's a good cooperation there. Those of you that have probably seen some of the so-called Eskimo games, one is the blanket toss, where the Eskimos are in a large circle and usually a young person gets in the middle, is thrown up in the air. The reason they did that was to look for whales. I mean, there are no trees to climb, so you get a young, nimble person with good eyesight and they can sight a whale. They don't need that anymore with now the GPS tracking devices. And you'll see in one of the pictures that, of course, the boat is traditional, but the paddle is a Sears Roebuck paddle. So there's and I think for me that's one of the things. Traditional naval architecture doesn't mean to say things are stuck in the past. There's combinations of those things that are particularly valuable. Moving on to one other example is West Africa, and I worked there in the early 70s, and you get these long open beaches but no harbors, big surf rolling in all the way from the Southern Ocean sometimes. And I was working on another project, but they asked me to go and look at a project that had been funded for a few years but not funded anymore. My boss is in FAO. And the project was that these large mahogany canoes were dugout canoes, so fairly wasteful of the material, it was thought. So they cut down the trees, sold the mahogany trees as a cash crop, and then imported marine plywood to build local boats, because these were big, heavy boats, and Europeans knew better about boats than the local people, obviously. And so I went there, and all the plywood boats were turned upside down along the top of the beach with nets stored under it. And I said to the local people, "But so you're not using?" "No, we're fishing today." So a little while later, these big dugout canoes came in with all the outboard motors installed. And I'm reading this previous report, and I'm looking for winches to move them up and down the beach. Well, in fact, they all went home and left two skinny kids. And these boats are banana-shaped, long overhang. Well, one kid sat in one end of the boat, the other one pushed it 2 meters up, and they moved 5-ton canoes up the beach in 30 minutes and went home. And they've been doing that for 3,000 years. And it's a very elegant mechanical solution for moving canoes up and down beaches. And so that was just another of the eye-openers for myself. And in many others. I worked in Madagascar for a while, and I know things about outriggers that the people who are designing trimarans for the Navy right now are getting wrong. And similarly, you'll see if you come at 4:30 in our footy racing competition that I have a small-scale carbon fiber version of a Dow rig that's probably a winning combination. So I'll hand you over to the next speaker. Thank you.
Thank you, Peter. You're up, Chris.
Great, thanks. Thank you, good afternoon. An honor to follow Peter. My interest in this subject, in fact, began with Peter's ethnotechnology paper in BC in '94. I am not an expert in kayaks, I'm an expert in asking why. And I wrote down the quote you just gave us, where technology comes before the science that explains it. And that's what I like doing. I really enjoy looking at the craft and saying, now why? That is the result of a very efficient, very effective process, but how can I translate that result into the language that I speak in 21st century scientific language? Because, of course, the indigenous craft are the result of the same physics. The water hasn't changed. They're the result of an extremely effective but slow evolutionary process. And yet we find myriad cases where the craft are wildly different. I grew up with a dugout canoe in Mexico. It's entirely different from the Greenland craft we see in front of us. It's quite different than the African craft. What were the constraints that were imposed on those craft that led to those design differences? And how can I explain, how can I look at the design difference and then back out, oh, I see, he was responding to a requirement like this. And if I were to take that requirement away from the boat because I'm going to make it in fiberglass, or I'm going to use it on the top of my SUV, then the boat will evolve this way instead of the way that it did. So let me try to say that in a little more detail. Obviously, this is an attempt to graph the evolutionary design process where one design leads to another, and we eventually seek out very slowly an optimal combination for a particular situation. But the graph, the shape of the landscape, the location of that mountain peak is going to be the result of a lot of constraints regarding the mission of the craft, the technologies available, the materials available for the craft, the seas in which she operates. And anytime I change those constraints, really I ought to re-evolve the design. But of course that's going to take generations to do. So how can I back out where those constraints have affected the design so that I can understand them? The design requirements, of course, in naval architectural terms are entirely consistent. Now this is by no means a comprehensive list of kayak or canoe design requirements. You'll find nowhere on here some of the concerns for the paddle hydrodynamics of these Greenland boats or for moving the boat on a beach in Africa that Peter was just talking about. But let me home in on just 3 of them that I think are strongly material driven, construction technique driven. And I'm going to highlight those just because I want to use this choice of material as a way of this why. Why did they do that? Why that feature on the boat? And there are myriad whys. I could spend hours asking why from stem to stern on these boats. But let me just take a couple of quick examples as an example of the mindset. And here's a picture I loved when I found this on the internet. Let me speak student for a moment. We teach you that ships are longitudinal beams, bending in longitudinal loading. And we teach you that there's a neutral axis on that beam at which there's like no load. Well, notice how this design has evolved where we put structural material at what we would call the shear strake, and we put structural material at what we would call the keel or the chine, and we have no shell plating at the neutral axis where I don't need it. And I have no shell plating on the deck because I'm going to design this boat so that the deck is not contributory to longitudinal bending, at least in the compression mode. Of course, I could load the deck when I put the boat in hogging. That's intriguing. But of course, what we will often do is we'll duplicate that geometry in sheet material, and we lose that advantage. And we end up with perhaps arguably a misapplication of the material, because now I've put material back at the neutral axis where in fact I didn't need it. And in fact, advocates of these craft will tell you that the native-built boats are better than any of the store-bought boats. I don't mean to steal your line, but you just said that to me, credit where due. You just said that to me before the meeting. I tried an approach just as just sort of for grins here. I'll show you the McKesson Trash Yak. This is a canoe that I built out of trash. It's the styrofoam packing materials that a bunch of IKEA furniture came in. And because I am not a craftsman, the body plan is entirely rectangles with right angle corners. But it has a scientifically designed sectional area curve with an optimal prismatic coefficient and an optimal location of center of buoyancy, according to Saunders' design curves, and a stability moment of inertia of the waterplane designed for my personal metacentric height goal. And as a matter of fact, it's a really sweet boat. That's in my pool in New Orleans, but I've had her in the bayous chasing the alligators and stuff, and she paddles really sweet. And I think she don't look half bad for being made out of trash in an afternoon. Okay, beam bending, geometry. Let me spell a little bit more about how I'm looking at the boats, and I'm saying, now why? How was this driven by a material consideration in this case? Let's remember how beams bend when I simply support them. They bend in a cubic curve between point loads. They bend like that gentleman is bending that frame in this birch bark canoe. In fact, in this situation, the shell is a membrane in tension stretched over this frame that is the result of a bunch of cubic splines. And I used to, as a boy, wonder why your birch bark canoe had that extreme tumble home at the ends, why it had some of these shapes to it. And looking at it with a bit of a scientific eye, I can immediately see. Now let's consider, for example, the shear strake beam in this case. There's a beam bent in a cubic curve via the application of some point loads where those transverse stiffeners are, transverse thwarts, members. And of course, if I take the thwarts away, that beam's going to try to snap into the straight line that I've dotted in there, bending like a bow and arrow. It's going to try to snap straight. By contrast, the frame in the middle, bent like the gentleman's knees, if I take the gentleman's knees off of it, it's going to try to snap straight as shown in the dotted line in this section. So what happens first is this side beam is loading that thwart in compression. That thwart is holding the side beam bowed out. That same thwart is holding the frame bowed in. In fact, I suspect that you could eliminate that particular thwart. Cleverly done, I wouldn't be surprised if those two loads on that thwart canceled out, and that the tendency of the frame to spring outwards and the side shell to spring inwards are canceling each other out. A very clever bit of design that allows you to make a very lightweight boat when I got lightly loaded members. I still ask why the shape of the ends of the boat, and I think I find the same thing when I start looking for cubic curves in the hull. Why is that point located there and not, say, there? And in fact, a lot of fiberglass canoes you can buy look a lot more like my blue line, and there's a reason for it. And that's because if I bend this as a bent sapling, if I release it, it's going to tend to spring, as I've shown in the dotted lines. If the only thing constraining that is the fact that I've tucked it in the pocket of an envelope, which is that stitched birch bark, obviously if I built the envelope the way the previous slide showed, the beam will just snap out of it. Bend a coffee stirrer and stick it in the corner of a normal letter-sized envelope and it'll pop out. Seal the envelope and put the coffee stirrer in and it'll stay bent. It's a result of a tension between the materials, the material properties, and what I'm trying to do in terms of fasteners, the fact that I'm going to stitch that member into a membrane-type hull, etc. All right, what am I saying? I find it very interesting to look at the craft, look at the geometry. The geometry was, of course, responding to requirements in maneuvering, buoyancy, stability, resistance, sea keeping, a raft of others, stealth, as I learned today, silence, fascinating subject on these boats. But the geometry was to some extent constrained by the available materials. The material selection, the production technology available. Do I have modern adhesives or am I doing this with rawhide thongs? Weight goals and durability goals. If we change the material, how will that free me up to come up with perhaps a better geometric solution or to even to understand the geometry that they came up with? The next boat I want to build after my trash shack, I have a hankering to go get some PVC tube and Tyvek house wrap and see if I can't build a skin boat out of PVC tube and Tyvek in an afternoon. Why not? It's an intriguing exercise. Sometimes structural material dictates geometry. We won't talk about this boat, but I think it's a great poster child for the subject. Thanks.